Hello everyone. So in this video, let us understand how to develop a Verilog code for 2 to 4 decoder using only NAND gate. So in this experiment, I am trying to develop Verilog code in gate level description. So gate level description is one of the feature of Verilog where we can instantiate gate primitives in the code. And very importantly, the basic need to develop Verilog code in gate level description is your digital design should be represented in the form of interconnection of logic gates. So 2 to 4 decoder is a combination logic circuit which consists of two inputs with four output, and we have considered one enable line here. Let us consider it is active low enable. That means whenever enable is 0, a 2 to 4 decoder will be in active state, or else it performs its function. Otherwise, whenever enable is 1, the 2 to 4 decoder remain inactive. And depends upon the combination of the input, any one among the four will be activated. Any one output among the four is going to activate. So the truth table shows the characteristics or behavior of 2 to 4 decoder. So here if enable is 1, system remains deactive. Therefore, irrespective of any input, output will be remain 0. And if enable is 0, system or decoder will get activated. Therefore, so the output depends upon the combination of input. Here if my input combination is 0 0, then y0 line will get activate. And if my input combination 0 1, then I'll get the output at y1. And if my input combination is 1 0, then y2 will get activate. And if my input line is 1 1, y3 line will get activate. So out of which we can formulate the logical equation. So each equation represent corresponding to each output goes like this. Suppose if I write a logical expression for y naught output line, which will be y naught is equals to enable bar, since that output will exist if enable is activated, and I1 bar, since I1 and I0 are 0 0, so the combination remains I1 bar and I0 bar. So this is the product term or expression for Y0 line. Likewise, we can also formulate the expression for Y1, Y2 and Y3. So essentially Y1 becomes enable bar, I1 bar, I0, because the combination is 0 1, and Y2 is enable bar, I1 and I0 bar, and at last the output line y3, so obviously it is enable bar, I0, I1 and I0. So these are the logical expressions corresponding to the output lines of the decoder. Now using this logical equation, we can represent that system design in terms of interconnection of logic gates. The same expression what we have seen in the earlier slide is represented in the form of interconnection of logic gate. So this is I1 line, I0 line and enable line. I hope you know how to represent those equation in terms of interconnection of logic gate. But the experiment expects to represent the complete information digital system only in terms of NAND gate. Therefore, logically it is modified. So for each output I have inserted one bubble, that means one NOT gate, and to obtain a proper logic, the output of each NAND gate is connected to one more NOT gate. Here, NOT gate is modified as NAND gate. So obviously, you'll get a corresponding output here called Y naught, and it is Y1, and it is Y2, and this is Y3. Okay, so where AND gate is replaced with NAND gate to compensate the logic. So the output of the NAND gate must be passed via NOT gate, and here NOT gate is replaced as NAND gate. And similarly, whichever the NAND gates which are used in the design are also replaced as NAND gate. NOT gates are replaced as NAND gate. Please observe that NAND gate should consist minimum two input. Therefore, while forming the NOT gate, both the inputs of the NANDs are tied together. Clear? Now, look at the design. So, identify the ports. So, your ports are I1, I0, and E. These three are the input ports, and Y0, Y1, Y2, Y3 are the output ports in terms of Verilog context. Whereas the output of the first NAND gate, let me call this as NAND gate 1. So, I'll call it as N1, NAND gate 2, N2, and NAND gate 3, N3. These are the instance name. Similarly, I'll give the instance name for this as N4 and N5 and N6, likewise N7. I'll make it as N10, N11, N12, N13, just for my reference. And inspect each gate here. If I inspect each gate, so the N1 NAND gate connected to the inputs I1, whereas output is neither the output, therefore it's not an output terminal, therefore I must declare it as a wire. So let me make it as I1B. I'll mark this wire as I1B. Likewise, I can also identify the output from the NAND gate 2 also must be declared as wire, so I'll make it as I2B. And the output from the NAND gate 3 also must be wire, therefore I'll declare it as I3B. Okay. And while inspecting N4 NAND gate, so where the inputs are either from the input or wires, input I1, I0E, or otherwise it is from I1B, I2B, or I3B. So the same thing applicable for NAND gate 4, 5, 6, and 7. You can inspect that. And whereas the output of the NAND gate N4 is not connected to the output port, therefore it must be a wire. It is an intermediate connection or interconnection between the element, therefore it should be a wire. So I'll make it as Y0B. Okay, so Y0B. Similarly, I'll make this wire terminal as Y1B, and I'll make this as Y2B, and this I'll declare it as Y3B. Okay. So look at your design. Your design essentially consists three inputs I1, I0, and E, four outputs Y0, Y1, Y2, Y3, and wires I1B, I2B, I3B, and also Y0B, Y1B, Y2B, and Y3B must be wires. Okay, this is the declaration part. Now let us try to simulate the same using Xilinx tool. So I use Xilinx tool to simulate this design. So I'll go to new project, create a new project. I'll give the project name as Decoder, and I'll keep this particular project in appropriate directory. I'll choose top level source type as HDL, and then specify the product category to which you must implement this design at the end. So I'll be implementing this product or this particular design in Spartan 3 XE3S50 device, and I'll take the simulator tool as ISC simulator. It's an inbuilt simulator, and my preferred language is Verilog. Click next, create a new source. So select Verilog module, and your module name should be the file name. So I'll make it as decoder underscore 2 to 4. So always module name or any identifier should start with alphabet. Do not start with number, and make sure that this particular file is added to the project, or otherwise we can also add in the later stage. Click next, specify the inputs and outputs. So in my design, you can look into the design. So we have inputs as I, I1, I0, and enable are the inputs, and outputs are Y0, Y1, Y2, and Y3. Y1, Y0, Y0, Y1, Y2, Y3 are the output. So select the output direction. So these are all the ports required for my design. Click next. So the same will be summarized here. Finish, and create directory. Click next, next, finish. Now look at the simulation screen. So here I'm going to develop my Verilog code. So already the Verilog file. So with the module name decoder underscore 224 is created with the following ports are declared: input I0, I1, I0 and enable, and outputs Y0, Y1, Y2 and Y3. Okay. So now I must declare the wires. So wires here, uh, wires are wire. Wire should be declared with the keyword wire, and wires are I designated wires as Y1B, comma I0, I0B, and designated as I0B, comma EB. So and also four more wires called Y0B, comma Y1B, comma Y2B, comma Y3B. Okay, these are all the wires required and identified in the design. Therefore, those wires are declared here. Now, simply just invoke NAND gate, and according to the design, okay, you have to interconnect them. So let me invoke NAND gate. First NAND gate instance N1. I'll specify the instance name as N1, and interconnection goes like this. Always for gate primitives, you must specify the output connection first, followed by the input. Your output for instance N1 is I1B. Okay, I1B is the output. My inputs are I1 and I1. Since both inputs are tied together, so I have to specify the input twice here, I1, comma I1. Since NAND gate except NOT and buffer, all the remaining gate at least consist at least two input. Therefore, simply don't write I1. So you must specify minimum two inputs. Since both inputs are tied together, I must specify it as I1, comma I1. Okay. Likewise, I'll take a copy of second NAND gate. I'll mark it as NAND. The instance name is N2. So I'm referring to the second NAND gate where output is connected to a wire called I2B. Okay, and inputs are I0, comma I0. Okay, just like that, you have to instantiate remaining NAND gates and interconnect. Okay, I'm going to deal with the three input NAND gate N4, N5, and N6. I'll declare or I'll call primitives NAND, primitive gate NAND with an instance name. Uh, or otherwise one more instance I have mixed here, one more copy. So NAND N3 where output is EB, enable B. Okay, and marked output as enable bar, and inputs are enable, comma enable, en, comma en. Likewise you instantiate all the remaining gates. Let us go for next section, that is three input NAND gate. So invoke NAND, instance name is N4. Connection goes like this. First you specify output. Output is Y0 B, and inputs are for this particular NAND gate. Inputs are I1 bar, I2 bar, and enable bar. Okay, I1 bar, I2 bar, and enable bar. Just look at your logic diagram and specify the connection. Okay, so this completes the invocation or instantiation of N4 gate. Likewise, you have to instantiate remaining gates and interconnect them. Okay. Now save your file. So this is the I instantiated remaining NAND gates. Okay, and now save your Verilog file and perform check syntax. Okay, check for if any typographical errors. So now the code is error free and perform synthesize. So synthesize is the process of conversion of your high level description or RTL description to gate level netlist. It pop up with a warning. Let us The warning is I2 is used but never assigned. Where fine, it's supposed to be. I have misinterpreted here. Why not be? It must be I1, I not. Okay, sorry, not bar. It is I not, and it is I not bar and I not. Instead of 0, I have typed as 2. So just let us correct and perform check syntax. Now perform synthesize. Here also it must be I not B. Sorry. Save, synthesize. Now this particular code got synthesized. If you want, we can check for RTL schematic. Okay. So this is the expected design, and if I look, all this particular design is how this particular design looks like. Okay. Now let us perform a simulation. Let us verify the functionality. So for that, create a new source. Take one more test bench waveform. Let me test bench waveform will be create with the name called test. Click next. Uh, Make sure that the particular design block mentioned here. Click next. Finish. Since it is a combinational circuit, I'll select combinational option. Finish. Now feed the input. So I'll keep enable 1 for a instance, or otherwise I'll keep enable 1 at last. Give the appropriate combination of input. Inputs are 0 0, then I naught is 0 1, and then 1 0. Okay. It is repeat. I naught is 0, it is 0 0, then 0 1, then 1 0, and then 1 1. Okay, these are all the combination I have given, and I given some random combination at the last. So I'll make 0 1, and also I'll make enable is equals to 1. Let us check what is my output. Okay, save this test bench waveform. Now go to process and source window, perform behavioral simulation, select the appropriate test bench waveform, and perform simulation. Simulate behavior model. Now let me perform zoom full view. Okay, so this simulation window provides me the all inputs combination what I fed, and the corresponding output. Okay, let I'll rearrange this. It is enable I1 I0. So if my enable is 0, I'll place the marker in between 100 to 200 nanosecond. So where my enable is 0 and my input combinations are 0 0, therefore I'm getting the output at Y0 line. Likewise, if enable is 0 and if my input combination is 0 1, I'll getting the output at Y1 line. And if my inputs are 1 0, I'm getting the output at Y2. And if inputs are 1 1, I'm getting the output at Y3. And at the last stage, although there is the input combination 0 1, outputs are 0 0 0 because enable is activated. So it is functioning as per my requirement. Okay. Thank you. Thank you for watching this video.